All right, so good afternoon, everybody. My name is Purcell, and I'm a third-year honors physics student in the co-op program from McMaster University. This summer, I worked for Triumph, and actually going to be continuing to work for them come January for my supervisor, Dr. Rich Helmer. So I worked on the Snow Plus experiment, which is located at Snow Lab, where I had another supervisor, Dr. Christina Krause. But Snow Lab is actually an underground physics lab, so because I was working underground, I got to have my full miner's training, so I'm now fully trained as a miner in Canada for the next 2 years. So in case physics doesn't go well for me, I can make a quick career change, which I'm prepared for. But I really just wanted to show this to show how much fun I really had working. It was just awesome to work on a real particle physics experiment. So now on to some physics. So my outline, I'm going to be talking about first the Snow Plus experiment, little outline, then neutrinos and double beta decay, a little bit about the Snow Plus detector, and then calibration, and then my own work, optical calibration, and then neck optics tuning, and finish with some conclusions. So the Snow Plus experiment is a large liquid scintillator detector experiment located underground at Snow Lab, as I said, which is approximately 2.1 kilometers underground. And it is a detector experiment. So basically in experimental particle physics, you have two types of experiments. You have detector experiments and you have collider experiments. So collider experiments, you're accelerating particles very quickly and then smashing them together. So you're sort of making particles that are exotic, that you wouldn't see on a day-to-day basis. Whereas detector experiments, you're just viewing things and then viewing particles, that would occur naturally using special techniques. So those are the two types of particle physics experiments. So Snow Plus is looking for neutrinos. So we search for solar neutrinos, geoneutrinos, reactor neutrinos, a couple other types of neutrinos, but our first most important phase is neutrino list double beta decay. So Snow Plus is actually the follow-up to the Sudbury Neutrino Observatory experiment, SNO experiment, which solved the solar neutrino problem. And the way we see our events is with liquid scintillator, which is linear alkyl benzene, which is just an organic liquid which gives off light when charged particles pass through it. So a little bit about neutrinos first. So neutrinos are leptons. They're from the standard model, there are 6 leptons. So we have our electron, our muon, and our tau. And then each of them has a corresponding neutrino to go along with them. And then each of them have an antiparticle as well. So the neutrinos only interact with gravity and the weak nuclear force. So because of that, they can pass through just about anything. And as well, neutrinos do have mass, but they have squared mass differences. And you can see in this image up here, this is showing how neutrinos oscillate between each other. So neutrino flavors have the ability to oscillate between. Now a little bit about double beta decay physics. So first of all, beta decay is where a proton switches to a neutron and is emitted in that decay. We have a positron or electron emitted, which is a beta particle, and then a neutrino or an antineutrino. And then double beta decay is for only 35 isotopes in nature can do this, and this is because beta decay is energetically forbidden. But they can undergo double beta decay, which is where 2 betas are emitted along with 2 neutrinos. So this has been observed, but it has a very high half-life. And then, so that is shown on the left here. And then on the right, we have neutrino list double beta decay, which has only been proposed theoretically. And this is where 2 betas would be emitted, but no neutrinos at all. And for this to happen, this would mean that the 2 neutrinos would have to cancel each other out. So it would mean that the neutrino is equal to the antineutrino. And this would make them Majorana particles. And this would be the first particle of this kind ever found. Now a little bit about the Snow Plus detector. So I'm going to start in and move out. So first on the inside here, you can see this silver bulb. That is an acrylic vessel. It's not silver. It is completely transparent. It is 12 meters in diameter. And in that goes liquid scintillator, which is the LAB, approximately 780 tons. So every event from this experiment occurs inside this sphere here. Now moving out, we have this sphere out here, which is a photomultiplier tube sphere. So there are approximately 9,500 PMTs surrounding the inner acrylic vessel. And this is how all of our events are seen with these PMTs. And then out even more, you see this big layer of rock, which is simply because the experiment is underground, so you have to dig out in the rock to get to it. And then in between these spaces that we have here and the space here, that is all filled with water, and that is for neutron shielding, so that when neutrons are emitted, they actually collide with the molecules of water, and that energy is getting rid of. So that really eliminates that background. So the topic of background sort of takes me into the calibration topic. So calibration is incredibly important. That's one of the things I didn't really know coming into particle physics, but it was really cool to find out just how crazy the amount of calibration that you really have to do to get an experiment to work. So calibration occurs before the experiment and throughout the experiment, and for many, many years. So Snow Plus collaboration is very large. There's over 100 people, but every member is working on a calibration task with multiple members working on the same calibration task quite often. So calibration is you need to really be able to understand your detector. And so therefore understanding the backgrounds and the events that you're actually seeing, so you can eliminate, or you can decipher between what you're actually looking for and the events that you're trying to get rid of, which are your backgrounds. So here you can see a photomultiplier tube that is a single PMT, is about this big. And so for optical calibration of those PMTs, the main tool we use is the laser ball. So the laser ball is about this big, and it is as cool as it sounds. It just shoots light out in every direction of a single wavelength, so you can place this anywhere you want in your detector, and basically the light hits every single one of your PMTs, and then that is how you optically calibrate them. So, and you can set the wavelength. It only hits or shoots out one wavelength at a time. So this is the calibration technique that I was looking at for my neck optics tuning. So here you can see the actual outside of the photomultiplier tube sphere, which is here, and this is the neck of the acrylic vessel, which is 7 meters long. So the question that I was trying to start to answer was, what is the difference in the attenuation of light between the neck acrylic, which is on the inside of this, and the acrylic of the acrylic vessel? So now looking ahead, here you can really see what the problem is. So here's the inside of the acrylic vessel. This pink pad here is on the inside of the vessel. And these circles here are PMTs. Those are actually 2.4 meters away from this pad. So that shows you how transparent that vessel really is. And now here is the inside of the neck. So you can see that that's dark. So this acrylic compared to this acrylic, there's a large difference. But we don't know what the difference in the light attenuation actually is between those two. So if say we have an event that occurs right around here, it could really occur anywhere, but say in the middle, call it a beta particle. So it occurs here, it shoots up, it hits off the neck, bounces around a couple times, it doesn't really matter, and shoots off, it hits a photomultiplier tube, say located right here. So when this happens, because of the scintillator, it's converting the particles that we see into light, which is how the PMTs detect them. So the light is actually, the energy of the light is lost up here in the neck because it's very dark. And then it still has some energy when it's seen by the photomultiplier tubes. So now your beta particle event may actually look like a neutrino event or some other event that you're actually looking for. So this effectively becomes a background that we're now trying to eliminate. So to start solving the problem, I had to look at solid angles, because this is how PMTs see their light. So I looked at snow data. Laser ball runs the calibration of that experiment in 2002, and looking at laser ball positions of 500 and 550 centimeters on the z-axis, where 0 is being the center of the detector. And I got this histogram called counts. So here on the y-axis, we have number of hits, which is the number of flashes that each photomultiplier tube receives from the laser ball. And then on the horizontal axis, we have PMT numbers. So those are just all the PMTs. You can see there's approximately 9,500. So I use this graph to make my own counts versus z-axis graphs. So these are really the heart of my work. So first of all, to explain, we have the same vertical axis as we just had in the counts graph before. The horizontal axis is the actual Z position of our detector. So here is the 12 meters of the acrylic vessel, and then the photomultiplier tube sphere extends to about here and down here. So that's why it's negative 800 to 800. And then the color is for the depth. This is actually technically a three-dimensional graph, a two-dimensional histogram. So this is occupancy, which is count divided by total number of flashes that each PMT receives in total, not just for one PMT. And so this is really how we get the amount of light that is seen. So to start, we can see that the top one, the 500 centimeter position laser ball run, has an exponential increase and then drops off just a little bit at the end, whereas the 550 increases, then dips, and then ends in an exponential increase instead of a decrease. So if we look at this, we don't really know why this is happening, so I went inside. You can see the 550 here and 500 be about here. So I went inside the acrylic vessel and was actually able to measure this area of the acrylic. And it turns out that right at the lower part of the neck, right here, there was an 8 centimeter thicker area of the acrylic that extends for about 11 centimeters. And so because of that, the position at 550, as you see here, the PMTs, which are right about here, are seeing this entire width of this extended area, plus a little bit more. So that's why you get the dip and then the increase at the end. Whereas the 500 centimeter position is only seeing the edges of this thicker area of acrylic. And then because of the PMT location compared to this laser ball position, it drops off at the end because it doesn't see past this extra thickness. This was very cool. Nobody had looked at this before, so I was excited by this result. But all this really shows is that some light is still passing through the neck. What we really want to know is the difference in attenuation of light. So to do that, I actually had to look at the difference in colors. So you can see here that there's color in the middle areas where the PMTs are actually seen, but it drops to purple and blue towards the end, which means the occupancy is going to 0. So what I really want to find is the difference between this color for where most of the PMTs are and the dropping off, which will give me the difference in the attenuation. So to do this, I had to look at solid angles, as I was saying before. So we have a solid angle function, which turns out to be sine alpha over r squared, where here's my alpha and here's my r, so both of those change for every PMT position on your z-axis. And so I can make that function easily as long as I have one parameter, which is big R, which is the center of the acrylic vessel to every single PMT. That's a basically constant radius. It varies slightly for every PMT, but that's not a big deal. So from that, I was actually able to get data for every single multiplier tube, write a function to solve for radius, and then graph them all on this histogram, which gives us the radii for every single multiplier tube. And as you can see, they're generally all in the same area. So to keep it simple for now, just to get my general attenuation difference, I just averaged them out and got the mean radius here, which is about 8.4 meters. So now I have all the parameters that I need for my function, and so I can put them all in and write my solid angle function, and then divide that function by my histogram I made, which will give me one line, which will be the attenuation of light through the acrylic vessel, and then another line, which will be the attenuation through the neck. And the difference between those lines will be the percent difference that I'm looking for. But unfortunately, summer ended, so I wasn't able to get this result just yet. But luckily, I'm going back in January, so I will be able to finish this task off and continue and keep getting this result more accurate. So just to conclude, the Snow Plus experiment will begin taking data in 2013, and these calibration tools are really, really important to make sure that the data we actually take is meaningful. So doing this optical calibration will allow the area of the acrylic vessel closer to the neck, allow the data that we take in that area to actually become meaningful, instead of whereas it had to be removed in the snow experiment. Getting this value into the actual database will allow this area to be included much more effectively. So it will really help out the experiment as a whole. And I just want to thank my supervisors again. Thank you all for listening. I had an awesome time this summer. I can't wait to go back in January. Thank you.
Thank you for that talk. Any questions?
This neck is, I assume it should be as small as possible to avoid this problem. When they built it, did they try to make it as small as possible, or?
When you're actually, the experiment is running, yes, it is completely sealed off, okay, because you can't have anything in there. But, I mean, you have to do work in the actual vessel throughout, or when you're actually before the experiment, setting it all up, the installation phase, so you actually need to get in there. So, like, a person has to be able to fit in there, and as well as everything else you need to lower in there. There's buckets that you actually have to lower in to get things inside, and it's like I've been in there. So, and when I'm inside, if I can't spread my arms out, there's no room. So it has to be able to get people in. So that's why, I mean, you make it as small as possible, but you still have to be able to get a person inside. Yeah.
We have one more question over here somewhere.
Well, I was just going to ask again, how deep underground is it again?
6,800 feet is most precise, so approximately 2.1 kilometers. So I guess it's actually 2,070 meters, plus then your additional distance, which is about 20 meters down, even deeper where the actual vessel is located. So this experiment is almost exactly 2.1 kilometers. Yeah, it's the deepest underground physics lab that's active in the world. It's one mine shaft, the same mine shaft that all the miners go down. It's pretty interesting, yeah, associating with that. Anything else?
Thank you very much, Ben.
Thank you.